Our next goal was to try to extract as much information as possible, to try to bridge the gap between our simulations and observations. And the way we want to do that is to convert our simulations into mock data products. We want to basically use the same tools that observers would try to derive physical properties from their observations with, and instead go the other direction. We want to generate mock images based off of our simulation data. This has been work that's been done with, again, collaborators here at the CFA, and in particular I want to point out contributions from Greg Snyder, who I've worked very closely with throughout this project. So I think this is generally what sums up this next section. We have observers who know what they're doing. They've got these large telescopes. They're actually very carefully analyzing their data. And then here I come along just checking. I just want to make sure that this is sort of being interpreted in the most meaningful way possible. What we're trying to do is not redefine the way that observations are interpreted, but to rather see if we can bridge the gap in terms of how we can talk to one another. So when you try to perform these sorts of comparisons, if you take the simulations at face value, we're actually speaking somewhat different languages when we talk to observers. In the simulations, what we have is physical quantities, things like, for example, particle masses. We can get a galaxy mass by adding up the stellar mass in all of the particles in our simulation. That is not what an observer actually does. An observer has information about the light that travels to us, and then applies a model to derive the stellar mass. So there's some ambiguity about how we should actually bridge this divide, all right? In most of the simulations most of the comparisons I've talked about so far, I've implicitly assumed that all of the quantities derived from observations don't have associated errors. In some cases, they have error bars associated with them, but they can have intrinsic errors. Just to give an example, if we look at the galaxy masses that are derived from from observations, a change in the IMF alone can be a factor of 2 in the stellar masses that are derived. And that's not really something that we take into account. In the simulations, we do not have that equivalent uncertainty. So what we want to try to do is talk about how we can convert into a language which is more comparable between these two ways of doing science. So specifically, we're talking about bridging this gap by applying stellar population synthesis models, applying star formation rate indicators and morphological proxies directly into the simulation so that we can apply the same analysis tools that observers would use on real data. Now, we're not the first ones to actually do this. In fact, there's been a fairly large body of literature that has used mock observations of galaxies to publish results. This is just one relatively recent paper by Javier Arguedes looking at the Aries simulation, and on the left you're looking at a mock optical image of this galaxy where you see star-forming regions and an older, redder stellar population. This is another paper by Greg Stinson where they looked at these magic galaxies, and again you see the different colors for where you have ongoing star formation, and the redder population corresponding to an older population of stars. And this is work by Federico Marinacci looking at the Aquila simulations using Arepo with a fairly similar feedback model to what we've applied, where again you see bluer star-forming regions with redder, older stellar populations. In general, when people publish these sorts of models, they do so for a dozen, or at best 2 dozen galaxies. They're not doing these for entire populations. And so what I'd like to show you is that not only are we now actually able to obtain relatively realistic galaxy morphologies in our simulations, we're able to do this for very large ensembles of systems. So this shows a sample of morphology taken directly out of one of our full feedback simulations. This is showing one galaxy viewed from 5 different viewing angles. This is showing another galaxy here with a bar, again from 5 different viewing angles, and then 2 different ones down here which have more elliptical morphology. Right off the bat, it's important to note that we're finding both disk-like systems and elliptical systems directly in our simulations. In fact, this has been very hard to achieve in the past. These are forming in the same simulations we've applied the same physics, and so we can ask questions about how these have actually built up their morphological diversity. All right, that's what's shown here. So here, if I take a population of 5 elliptical galaxies at redshift 0, I can directly now trace back their evolution to redshift 2. One thing to note, this is showing rest frame GRI bands, Sloan images. So at high redshift, these galaxies appear bluer, and that's because they have higher star formation rates. Another interesting point is that if you look at these systems, 4 out of 5 go through what appear to be relatively major mergers before they reach redshift 0. And frequently, you actually see that that merger event is associated with converting what would be otherwise disk-like morphology into a spheroid. So we're now actually able to directly probe the transition of disk-like morphology into elliptical morphology directly in these simulations. You can also look at the assembly of disk galaxies. Here is looking at 5 different disk-like systems traced back to redshift 2. Now these are less massive systems, and so their merging history is somewhat quieter. But you do still see there are some mergers, and that's interesting that these galaxies are able to maintain their disk appearance even after going through a relatively major merger. But in general, the formation histories of these disks tend to be a bit quieter. So there's a lot of really interesting information about how, for example, mergers or in-situ star formation is impacting morphological diversity. But really, the power of these recent simulations is not in doing this for 5 or 10 systems, but doing it for large ensembles of systems. So this is now showing about 25 galaxies from one of our recent simulations, traced out to redshift 2 with relatively fine time stepping. And we can just pan out to look at the galaxy populations that we actually have here. This is looking at a 25 megaparsec cubed volume, showing the 100 most massive systems. They're all fairly well resolved, and we have interesting mergers, interesting morphologies building up in all of these systems. For our most recent simulations, we did 75 megaparsec cubed volumes. In that, what we have is 7,000 galaxies, which are fairly well resolved. 7,000 galaxies with stellar masses above 10 to the 10 solar masses. We have more than 10 to the 4 star particles. That means we have fairly well resolved morphology. We also have some groups and clusters available in these volumes, which means that we can study things like what the environmental impact on galaxy colors or galaxy morphology is. Now, to show one application, one way we can actually use observational tools to reanalyze our image pipeline data. One game we can play is to rederive stellar masses for our mock image catalog. We already know the intrinsic masses based off of the simulation, but now we've created mock images so I can rederive the stellar mass I would assign to this galaxy as if I didn't know it in the first place. So we use the SED fitting code FAST to do this. What we're doing is effectively assuming a star formation history, in this case an exponentially declining star formation history, and then from that finding the best fit metallicity and star formation timescale to figure out what this galaxy's mass is. So this shows the fast mass against the subfine mass. This is basically the intrinsic mass from the simulation. And what you find is that we get a fairly good one-to-one correlation. However, this is actually shown over 3.5 orders of magnitude. If we instead look at the ratio of the fast mass to the intrinsic mass as a function of intrinsic mass, you do see there are some residual trends. And this, I think, is actually really interesting to note. You wouldn't have been able to do this if you didn't know the galaxy's intrinsic mass. Turns out the origin of this difference is actually fairly easy to tease out. We can look at the metallicity that FAST is assigning to these galaxies, the metallicity that the SED fitting codes thinks these galaxies have. In fact, there's a fairly clear difference between the metallicities that are found in this cloud versus what's found here. So if I pop back, you'll see there's kind of a relation of galaxies here, and there's another cloud of galaxies here. That's caused by different assumptions about the metallicity in the SED fitting models. If I look at the intrinsic metallicity, the metallicity from the simulation as a function of intrinsic mass, I find a relatively constant distribution. And so what's happening here is that FAST draws upon a set of stellar population synthesis models that have discrete metallicities, and they jump in fairly large intervals. And so what happens is that when I jump from one template to the next, I am moving in the right direction. These galaxies do have higher metallicities, but that discrete jump actually causes a kink in the masses that I'm deriving for these systems. If I come back here and rederive masses under the assumption of one fixed metallicity, this becomes a single relation. So I think that using this image pipeline data, there's actually quite a lot of science that we can do, and we've really only begun to scratch the surface. One thing that we can do is the SED stellar mass fitting. We find that factors of 2 errors are common. Overall, it does fairly well. Factors of 2 errors are common, and there are residual trends largely from the discrete metallicities in the stellar population synthesis models. You can ask questions about whether we get the disk elliptical fraction right, and Greg Snyder's working on this by using non-parametric fits for the galaxy images. We're also doing visual classification with Galaxy Zoo. We're going to upload a large fraction of our galaxies to the Galaxy Zoo project and have citizen scientists classify their morphology so that we can compare directly against visually classified survey data. And then we have other things that we can test, like, for example, how the high redshift merger rate is impacted by blurring of the images through low signal to noise or PSF blurring. So we can actually take our redshift 2 data and degrade its quality till it gets to observationally realistic level, and then see what fraction of mergers we're actually picking out. So these image catalogs are going to be made publicly available, and that's the way we hope to do science here. We're hoping that we can do some set of these projects ourselves, but that observers who have tools in place to already quickly analyze survey data can easily adapt to also using these FITS files that we're providing through our image pipeline to rederive some of the observational quantities directly from the simulation. This has been set up with an SQL database that's hosted on an external server. We're now able to serve up the data directly from Odyssey, though. And so we can basically use our supercomputer here at Harvard to serve up data to people throughout the world. We've got pre-made PNGs, which can be used for visual classification, and we've got the raw fits data, which allows people to look at these galaxy images in 36 different bands. So we're quite excited about the science that can be done there. I think that over the coming years, as simulations get larger and larger, and as survey data gets larger and larger, this might be the most powerful way that we can draw even-handed comparisons between these two types of science.